Hello and welcome to this film, which is all about analysing mass spectra. It's the third in a series of films about atomic structure in the standard level IB course, and hopefully you've seen the second one, which is all about how a mass spectrometer works before you watch this. If you haven't, it's not the end of the world, but it will give you a bit more information about how we're getting the graphs that we're going to look at here. Okay, so hopefully by the end of this film you'll be able to use the mass charge ratios and relative abundances that we can get from a mass spectrum to calculate the relative atomic mass of an element. And not only that, but you'll kind of be able to do the problem in reverse, and you'll be able to use the atomic mass of an element to determine what the relative abundances of the isotopes were. And hopefully you'll also understand what all these terms mean. Okay, let's start off by actually looking at a mass spectrum, because I said in the last film that we would. This is the mass spectrum of carbon. When I say that is the mass spectrum of carbon, what I'm saying is if we put a sample of carbon, naturally occurring carbon, into a mass spectrometer and vaporized it and ionized it and accelerated it and so on and so forth, then the computer would be giving us a graph that looks like this. Now you might remember that carbon occurs in nature as three different isotopes: carbon-12, carbon-13 and carbon-14. What this graph is showing us is that an awful lot of those carbon atoms have a mass of 12 compared to the ones that have a mass of 13. And in fact the ones that are carbon-14, they're not even showing up on this graph because it's not high enough resolution. There would be a peak here, but it's too tiny for us to see. Okay, now what we can do by looking at our graph here, or rather by getting our computer to put some numbers to this, so in other words to put percentage on the intensity of the peaks, then we can find out that 98.9% of all carbon atoms have a mass of 12. Okay, 1.1% of them have a mass of 13, and less than 0.1%, because if you add these two up they actually give you 100%, so some insignificantly small number weigh 14. Okay, and strictly speaking, this axis shouldn't have just atomic mass units on it. It should say m/z, which is a mass charge ratio, which you probably saw on the mass spectrum that we saw in the last film. You might remember me saying that the charge of the ions moving through the spectrometer is highly likely to be 1. So if you take the mass in atomic mass units and divide it by +1, then that is the same as the mass, right? It is possible that you will get particles with a charge of +2 moving, in which case, for example, I might expect to see a peak at 6, which is all the carbon-12 atoms that accidentally got turned into 2+ ions, because that would be 12 over +2. But remember, this is a very unlikely occurrence, because it's like being struck by lightning twice. If you're in a gas, if you're an atom in a gas and you're moving through a beam of electrons, it's unlikely that you'll get ionized twice. Anyway, so the problem here is to try and find the relative atomic mass of carbon using these mass charge ratios of the isotopes and the percentage abundance of each isotope. So these numbers here are the percentage abundance, how likely they are to occur in nature. Okay, now remember what the relative atomic mass is. This is an extremely important definition to know. Okay, it's the weighted average mass of all the isotopes of an element. Okay, so how do I find the average mass of a carbon atom? Well, if I know that if I had 100 carbon atoms, 98.9 of them would weigh 12. So in other words, I could add up the mass of all the carbon-12 atoms in my sample. If I had 100 of them, they'd weigh 98.9 times their mass. I could add to that the mass of all the ones that weighed 13, and that would be 1.1 times 13. I ought to have some number here for my carbon-14 atoms, but we're saying that the percentage of them is insignificantly small, so they're not going to contribute to the overall mass. Okay, now that is going to be the total mass of all the atoms in my sample. If I want an average, I simply divide that by the number of atoms in my sample, and that's 100. And if I do the maths here, then I find that that's 12.011. So there is the relative atomic mass of carbon, and we found this by looking at a mass spectrum. When I say we found it, the way that humankind first discovered that this was the relative atomic mass of carbon was to get a mass spectrum and to analyse the numbers from it. What we've done is we've looked at the relative abundances, combined them with the masses to find an average mass. We're going to do exactly the same thing now, but we're going to do it using just numbers written down instead of a mass spectrum. We're going to do it using lithium, and we're also going to use it. We're going to do it using relative abundances that aren't percentages. Okay, but it's a simple problem in the same way that the last one was, because all we're doing is finding an average mass. Okay, now our relative abundances here add up to 12. I could turn these into percentages first. So 0.9 out of 12, I could turn that into a percentage, and then I could do this problem in exactly the same way as I did before. But if these two add up to 12, then I could imagine having a 12 atom sample, in which case 0.9 of my 12 would weigh 6. And to find the total mass, I'd add that to the 11.1 that weighed 7, and then I'd divide that by 12. Okay, and if I do the maths here, I get 6.925. Now, there's a useful check to see if you've done these things right, whether you're using percentages or not, and that is to say to yourself, right, well look, this one here is much more abundant, so the average mass is going to be much closer to 7 than it is to 6. And so it is, so that's a useful check that you've done something right, at least. Okay, now the last problem that we're going to look at in this film is kind of the problems we've looked at up to now, but in reverse. And the nasty thing about this is it involves some algebra, but it's not too tough. So what we've got here is we're told that rhenium has two isotopes, 185 and 187. That rhenium's relative atomic mass is 186.2, and we're going to try and find the relative abundance of those two isotopes. Now, remember, if we were told the relative abundances and we were finding the relative atomic mass, we'd be taking the one that weighed 185 and multiplying it by some number, and adding to that some number times 187. Well, we haven't been told the relative abundances. If they were percentages, we'd be dividing that by 100, and if we did this, we'd find it came to 186.2. Okay, we don't know the relative abundances, but we could imagine that the relative abundance of that one was x, and if we did that, then the relative abundance of this one must be 100 minus x, right? And I can multiply this out and end up with 185x minus 187x plus 18,700 divided by 100, but let's take that over to the other side and multiply this by it, and that would be 18,620. Okay, and if I simplify this, I'll get minus 2x equals minus 80. And in that case, x must be 40. Now what was x? Well, x was the relative abundance of the 185 isotope. So this one must be 40%, and this one must be 60%. Okay, a little bit of algebra there. I've kind of missed a few steps out of the working there, but hopefully that didn't upset you too much. And that's all the kind of problems you're likely to see with the data from mass spectra. Just one thing to look out for is this thing that I've touched on before, where ions don't end up with a +1 charge. Now, I could end up with a slightly odd looking spectrum. Let's say I had a pure substance. So by pure substance, I mean I'm putting in atoms of only one type. So let's say I had carbon 12, just pure carbon 12. I ought to expect a peak at 12 with a relative abundance of 100. However, I might get another peak at 6, because remember this axis is a mass charge ratio, and the fact that this peak here at 12 corresponds to the atomic mass relies on the fact that the ions have a charge of +1, because remember what the mass spectrum tells us is the mass divided by the charge, which should be +1, right? But it could accidentally be +2. I suppose conceivably it could be +3, but that's so ridiculously unlikely that even the highest resolution mass spectrometer is very unlikely to pick that ion up. Okay, hopefully by this stage you understand how we can use mass charge ratios, so that's the atomic mass of the isotopes moving through the mass spectrometer, and the relative abundance of those isotopes to calculate relative atomic masses. And you can do the problem in reverse. You can predict what the relative abundance of isotopes will be if you know what the masses of those isotopes are and what the relative atomic mass is. Hopefully the maths in there isn't too tough, but if you've got any questions you want to ask, or if you think I've made any mistakes in my maths, which I often do, then please feel free to post a comment on YouTube or come and let me know.